Okay, in this video we're going to be looking at just a few more sample problems out of Chapter 18, the Energy chapter for rigid bodies, and Chapter 19, the Impulse Momentum chapter for rigid bodies, introducing angular momentum. So the first problem we're going to look at, let's just jump over here to the picture, and we will maybe make note of some of the numbers, and if you want to work this on your own, just do a quick pause and print this screen. What we have is a drum or a wheel, or I might call it a yo-yo. It's very yo-yo-like. Pinned at its center, cord wrapped around it. We have a weight hanging down. This weight will, of course, cause this drum to spin. And what we have here is a handbrake, where someone will impose a force here at point D on a lever that's pinned to ground here. And so the force is amplified because of the lever action. And the question will be something about how the braking action works and what kind of speeds we might get, etc. So let's see what the details of the question are now. The drum has a mass of 50 kilograms, radius of gyration of given. If the 15 kilogram block is moving downward at 3 meters per second, that's to start, and a force of 100 newtons is applied. Determine how far the block descends from the instant the brake is applied until it stops. Neglect the thickness of the handle. The coefficient of friction is given as 0.5. And the key thing that makes this a Chapter 18 problem and not a Chapter 19 problem is determine how far the block descends. That's a distance, because what we have is changes in velocities and two different locations of interest and a distance that matters. And so a little bit of preliminary work. If we look at this picture, what we're going to want to do is, for a 100 Newton force applied here, we want to do the statics to find out how much normal force is being applied here, and then we can use friction equal mu times n to find out how much friction is being applied there. Then we also need to take a look at how much distance does this friction go through, how much distance is the friction applied through, because we will have the block falling a certain distance, but the block is attached at a different radius than the brake, and so because the block is at a small radius, it'll travel a small distance. The perimeter that gets rubbed by the friction pad will be larger than the distance that the block moves, and so we'll have to work out that kinematics as well, and so we'll see that in just a second. And so first thing that we will do is sum moments about the pin and set that equal to 0. That's a statics problem, and we will have a normal force between the disc and the brake handle of 0.5 moment arm, and we will have the applied force acting through a 1.25 moment arm, and so the 100 Newton load is amplified into a 250 Newton normal force. And because friction, kinetic coefficient of friction is 0.5, then we have a 125 Newton friction force that is acting over a certain distance to bring this thing to a stop. Now, ratioing and distance S is going to be the distance that the block descends. Then we're going to call S prime will be the perimeter distance that rubs on the brake pad, and it's going to be a larger number, and the brake pad rubs at a radius of 0.25 while the block pulls on the string out at a radius of 0.15, and so that ratio will also ratio the distances. So however far our block moves, S, the friction pad will be rubbing a distance S prime. And now we're ready to go to our work and energy equation, and we're going to say we are starting off with some initial T1 because we're moving, and we can either view gravity as potential energy or work. This example problem came out of the early part of the chapter where potential energy was treated as work. We can do it any way we like, but clearly that friction is going to go in as a work term. Okay, and so let's look at some of the other data that was given, specifically radius of gyration of 0.23 And so our energy term for the disk is going to be 1/2 I, so there's mk squared, omega squared. Now this is the speed of the block initially divided by the radius the block is moving, so this is just a V equal R omega relationship, where V was given as 3 and R was given as 0.15. So this is a 1/2 I omega squared term, and this is a 1/2 m V squared term, and the mass of that block was given as 15 kilograms. So 1/2 I omega squared plus 1/2 m V squared plus work done by gravity, which is mg times h, the distance that the block falls, being called s in this case. So that's positive work done by gravity. Then we're going to have negative work done by friction, and that's going to be a minus 125 newtons of friction force acting through this same distance s, scaled up by a factor of 0.25 over 0.15. We've already talked about that. And then we're going to come to a rest at the other side of the problem, and we have basically put our gravitational potential at the top of the problem and said the reference is at the bottom of the problem. So solving the one equation, one unknown problem gives us a falling distance of 9.75 meters. And probably the key difficulty of this problem is right here, realizing that whatever distance this falls, s, the rubbing distance might be multiple revolutions. Okay, multiple revolutions is going to be an s prime, and that rubbing distance will be larger than the falling distance. And that was problem 18-8. Problem 18-12. Let's take a look at the picture first. And we have another yo-yo. And this time the yo-yo is going to be rolling downhill in some kind of a situation while it is constrained to be tied to the rope, which is wrapped around a smaller radius. And so we'll have to look at the details of the problem to see what's going on. But what I want to do is explain some of this geometry right here first, and indicate that we are going to have slip right there. It's not going to roll without slipping. Why? Because it is in effect rolling without slipping. Here, that is a no slip. And in a sense, this disc behaves as if it's rolling down the rope with no slip. And so at every point on the disc where we're leaving the rope area, where we're leaving tangent, the tangential speed of the disc must match the tangential speed of the rope, and that is 0. And so this is also the instant center of this block as this wheel as it's traveling downhill. So we can almost view this as a disc that is rolling on a rail, maybe a wooden rail, but it turns out that disc was actually larger, and it had material that was down below that rail, and that's the instant center. That's where we're rolling with no slip. This system behaves very much like that system, except now we put some kind of a potential friction connection right there. Okay, so let's look at the details and the numbers. It says the spool has a mass of 60 kilograms, radius of gyration kg of 0.3. If it is released from rest, determine how far the center descends down the smooth plane before it attains an angular velocity of omega equals 6. Neglect friction and the mass of the card, which is around the central core. Okay, and the very next problem, 8-13, will then admit friction, which is nice because, again, we have to do a little bit of kinematics to find out over what distance the friction asks. And so we will use a working energy form, and the only thing is we'll be treating the gravitational potential as a work term. And so we are starting from rest. Therefore, our kinetic energy is 0. And then we will have our gravitational potential. One way to view this is at the highest point in the problem. We have a mass of 60, so it's a weight of mg, 60 times 9.81. We're on an angle of 30 degrees, and so the vertical distance that we will fall through will be our total travel distance, s, times the sine of 30 degrees, and that's the only thing we have on the left-hand side of the equation. And then on the right-hand side of the equation, our gravitational potential will be at the low spot, and that will be our reference point. So all we're going to have is kinetic energy, the 1/2 I omega squared plus 1/2 mv squared. And let's look at what these numbers mean. That omega is 6. So 1/2 I, which is mk squared. So 1/2 I omega squared plus 1/2 m. And since v is equal to r times omega, with that r being the 0.3 distance, the small distance for the rolling. So the kinematic equation is v is equal to r omega, and then v squared would be our final energy piece. This is a one equation, one unknown, where s is the only unknown in the problem. Solve for s of 0.661 meters, where we start from rest, and we have no slip here, so very slippery surface, and it takes us this distance to achieve an angular velocity of 6 radians per second. If we add in friction, just as in the earlier problem that we saw, is that this will travel a distance, but the friction distance will be different, but it'll be based on the instant center. And then I believe in this case, we'll see the numbers in just a second, that the friction distance will be smaller than the travel distance because of that instant center right there. Okay, and so working out the kinematics, SG, center of gravity, divided by 0.3 is equal to SA over 0.5 minus 0.3, and that 0.5 minus 0.3 is a 0.2. What are we saying here? We're saying that an S is equal to an R times the delta theta, but the delta theta, oops, you can't see that, so S is equal to R times delta theta, but for this wheel as it travels, the delta theta for both G and A would be the same. So delta theta is equal to S over R. And so S over R is a constant at both point G and point A. Here's S over R for point G. Here is S over R from the instant center for point A. And so we then have a relationship for how SA relates to SG. And SA is 2/3 SG. So the friction distance is actually smaller than the travel distance in this case. Okay, now we want to find out, so we're going to be able to deal with this friction. We're going to learn the normal force so we can then do a mu times n eventually. So sum of forces in a y direction, which is acting perpendicular to the hill, will be a normal force acting minus the component of gravity down perpendicular. And so let's see, let's jump over here and look at a free body diagram. Okay, we have the y direction, we have the normal force, we have a component of gravity, we have rope tension parallel to the hill, we have friction parallel to the hill, and so summing forces in the y direction, of course, is only the normal and the gravity piece. So we have the normal and the gravity piece, and we learned that the normal is equal to 509.7 newtons. And now we're going to work the energy problem, and the energy problem will be very similar to the previous one, but now we add in the friction. And so we have, starting from rest, and we have the mgh for the center of gravity, just as exactly what we had in the other problem. And so this is the distance the center of gravity travels. And then we're going to have work done by friction. The work done by friction will be the friction force, mu n. There's the friction force times the total distance that the friction force will act through, which is 2/3 of Sg. And so we have our gravity energy, we have negative friction work, and then finally we have our 1/2 I omega squared plus 1/2 m v squared, just as we did in the other problem. So all we did from the previous problem is add in this friction term, and because of the friction term it should take longer for us to reach a given speed, and so it says the center of gravity, when we solve for Sg out of this equation, the center of gravity will travel 0.859 meters down the hill before it reaches a speed of omega equals 6 radians per second. And so it took a bit longer because of the friction. Okay, those are the only Chapter 18 problems I've chosen to look at beyond the homework. Now I've got a few Chapter 19 problems. Okay, and what we have is a backspin kind of problem. Those are often quite interesting. So we have a bowling ball traveling to the right, but rather than rotating in a coordinated manner, such as that, traveling to the right and rotating clockwise, we don't have that at all. We are rotating with backspin, and a backspin omega of 10 radians per second. So we're traveling forward but rotating with a backspin. Now eventually friction is going to reduce this velocity, and friction is going to reduce the omega. And as they're both heading down, because the friction will be countering the velocity and countering the omega, and at some point they will reach a coordinated v equal r omega. Actually, at some point the ball will stop rotating in the back direction and eventually start rotating in the forward direction because of the friction. So let's see what we're asked for in the problem. The ball is cast on the alley with a backspin of that, and the velocity is given also. Determine the time for the ball to stop backspinning and the velocity of its center of mass at this instant. The coefficient of kinetic friction between the ball and the alley is mu k equal 0.8. So what we're going to have when we stop backspinning is we will have a ball that will have some velocity, but it will have, so v equals something, but it's going to have an omega equals 0. What does that mean? That means that the ball is sliding on the floor at that instant with some velocity but no omega. Now that friction will actually continue until as the ball travels to the right, it will begin then from omega equals 0. Sorry you couldn't see that. Let's move that down. So what we're solving for is ball traveling forward, but omega has gone to 0. But that's not the end of the story, because we still have friction happening with this velocity, and that friction will then get the ball spinning in the coordinated direction, but it's going to take a little while for the omega to get large enough while v is heading down, so that finally we will reach a v equal r omega equilibrium. But we weren't asked about that. And so let's take a look again, the details of the problem. We have the ball, we know the velocity, we know the backspin. Determine the time for the ball to stop backspinning, which I assume means omega goes to 0, and the velocity of its center of mass. Okay, and so first of all we will go and look up from the back of the book the I about the center of a sphere. It turns out to be 2/5 mr squared, and so we have a 0.02 kilogram meter squared mass moment of inertia about the center. I think what the author does in this next thing is a little bit silly. He is doing angular momentum in the vertical direction. I'm not sure why he didn't just do sum of forces in the vertical direction is equal to 0, since our mass times acceleration in that direction is 0. But let's look at how he does it anyway. So our starting linear momentum in the y direction is 0. We're not traveling in the y. And then we have a normal force acting in the y direction over time. That'd be one impulse. And we have gravity acting in the vertical direction through that same amount of time. And so this says n times time is equal to gravity times time. The times cancel, and we come up with the normal force is equal to the gravity force, exactly what we would have gotten here. That's probably I would not recommend doing it that way. That's silly. But we get a normal force which is equal to let's see, what did we have? We had a 5 kilogram times the 9.81 for gravity. So that's the 49.05 newtons. Now we will do angular momentum for the ball. And our angular momentum is going to be I times its initial omega. And let's see, now we've got to look very carefully and do this right. This is about point A. And to get point A, you need to look at the diagram that we have here. So this is our sphere. Point A is the contact point, which is the instant center. And if we're going to do angular momentum about point A, we're going to have both our moment of inertia, I omega type term, but we're also going to have a moment of the mass times mv type term. So m is 5 and v was also 5, so mv is 5 acting through a moment arm of 0.1. And so our total angular momentum is I omega, and that would be in the backspin direction, and we're going to call that backspin direction positive. If that's the case, then the moment of this mv about point A is going to be a negative number. And so we're going to say minus mv times its moment arm. And that's all we have. There are no angular impulses in here. Why? Because we're taking our moments about point A. Then the friction terms pass through point A. The normal force passes through point A. The weight passes through point A. So all of those disappear. And so we have I omega, the moment of mv, and then on the right hand side we're going to have, and this says that any impulses were 0. On the right hand side, the only thing we're going to have is our mass times the velocity, and taking through the moment arm of 0.1, the radius. So the moment of mass times the velocity, still negative because of the coordinate system that we chose. Okay, and then looking at this thing, our only unknown is our final velocity. When this thing stops spinning, we still have a velocity to the right of 4.6 meters per second. And we still don't know how long that took. So now what we're going to do is a pure linear momentum of the ball. And we'll have a starting linear momentum. We will have the linear impulse of the friction, and then we'll have a final linear momentum. And so our starting momentum is a mass of 5 times the velocity of 5, and then our impulse will be 0.08, that's the coefficient of friction, times the normal force, times time. Okay, so that would be our integral of a constant force dt. That constant force is 0.08 times 4905. And then finally, our final momentum that we learned from the angular momentum equation would be mass times velocity of 4.6 that we got from the previous step. And so our time is the only unknown in the equation, and we solve for time of 0.51 seconds. And so that answers the question, how long for the backspin to stop? Another interesting question would be, how long before they become coordinated? And coordinated, we don't know what velocity that will be. We don't know what omega that will be. We just know that coordination would mean V is equal to R times omega. That would be an interesting problem. Okay, a mildly practical problem. A car is going to hit a lamppost, and we're going to have some video data on how quickly the lamppost rotates, and we've got some geometry data about the lamppost. And the question is, how much impulse was imposed on the car? And so often during car collisions we'll talk about impulses, not forces. So you got a lot of words in the problem, but the solution is very short and simple. It says the car strikes the side of a light pole, which is designed to break away from its base with negligible resistance. From a video taken of the collision, it's observed that the pole was given an angular velocity of 60 radians per second when AC was vertical, when the pole was vertical. The pole has a mass of 175 kilograms, a center of mass at point G. We'll come back, well, let's slide over. So center of mass at point G, which is 4 meters. Okay, let's see, where were we? And a radius of gyration about an axis perpendicular to the plane of the pole assembly and passing through G of kg equal 2.25 meters. Determine the horizontal impulse which the car exerts on the pole at the instant AC is essentially vertical. So before it's rotated significantly, what is that impulse? And so we're going to use angular momentum, and we're going to focus on the pole only. Now there will be canceling impulses between the pole and the car. Whatever the pole does to the car does to the pole. But we're leaving the car out of the system, focusing entirely on the pole. And so we're going to say that the starting angular momentum of the pole plus any angular impulses applied is equal to our final angular momentum of the pole. And since the pole is starting from rest, not rotating, our initial angular momentum is 0. And then the angular impulse coming from the linear impulse will be the moment of the linear impulse. So here is our linear impulse. That's what we're trying to find. And that linear impulse will be producing a moment about the center of gravity. Looking over here at the picture, we're hitting it at a 0.5 meters above the ground. Center of gravity is 4 meters from the ground. So the impulse occurs at a distance of 3.5 meters from the center of gravity. So the moment of the impulse about the center of gravity is here. And then finally, we will have a 1/2 I omega squared. I'm sorry, not a 1/2 I omega squared. We're going to have an I omega. And so our I is going to be mk squared. So m of 175 and k of 2.25. mk squared, making this I, and making that the omega that was given. And the only unknown in this problem then is that linear impulse, which came from the car, of 15.2 kilonewton seconds. So if the impact duration took an entire second, which it almost certainly didn't, it occurred in much less time than that, then 15.2 kilonewtons. As the impulse time goes down, the peak force goes up. And for the data that we have, that's unknowable. Okay, finally, sort of the ice skater kind of problem, or man having fun in a rotating chair with a couple of weights. So we've got man sitting in a chair. He's spinning at 3 radians per second of initial speed. He is holding these weights out at a distance of 2.5 feet, and he's going to pull them in, and we're going to wonder what his new new speed will be. And he is fundamentally changing his own moment of inertia by moving the weights in. And so, man sits in the swivel chair, holding two 5-pound weights in his arms outstretched. If he's rotating at 3 radians per second in that position, determine his angular velocity when the weights are drawn in excuse me, and held 0.3 feet from his axis of rotation. Assume he weighs 160 pounds and has a radius of gyration of 0.55 about the z-axis. Neglect the mass of his arms and the size of the weights in these calculations. Okay, and so what we can do, we're going to want to calculate his moment of inertia, and then we're going to do a conservation of angular momentum. And his moment of inertia when he has the weights out far will be his mass, weight over gravity, times radius of gyration squared. So this would be I of the man. Now we do I of the weights, and it will be 2 times the mass of the weight times the distance of the weights from the axis. So 2 times m times r squared is equal to a total of 3.44 slug-foot squared. Okay, and let's see, this is an mr squared term. We haven't really dealt with point masses, but a point mass away from an axis would have a moment of inertia of mr squared, and we have 2 of them. Forgive this cough. I'm not sure why it came up, but my video system doesn't let me pause, so I'm just going to keep on cruising. Okay, finally the man brings in the weights and lowers his moment of inertia. Look at those numbers. He lowers it significantly. And so everything here unchanged. Everything here unchanged except the distance of the weight from the axis. It makes a huge difference in the moment of inertia. And now we will say that our conservation of angular momentum, because there are no angular impulses happening when we consider the system to be the man and the weights. And so our starting angular momentum is I omega, and omega was given as 3. Our final angular momentum is I omega, but that omega is unknown. This is one equation, one unknown, and we can solve for that omega of 6.75 radians per second, and so we have more than doubled our rotational speed. And that ends the problem that I am working on chapters 18 and 19.